Now that you know everything there is to know about virtual memory, let's go to the last part of our lecture, which is the translation Lookaside buffer. So what we arrived at is this machine that has now address translation before to turn virtual addresses into physical addresses to access the instruction cache, and again address translation to turn virtual addresses into physical addresses before the data cache, and we have page table walkers that can go and fetch that translation. So every cycle, what we're going to do now is we're going to load an instruction. So the program counter is going to provide the virtual address that is going to go into our address translation block, our MMU. And what it needs to do is it needs to go over to DRAM, run a page table walk to go and get what the actual address translation is. That's going to check for a protection violation. So if we have a protection violation, we're going to go throw an exception, invoke the operating system to handle it. And again, we're going to also check for a page fault. If there is a page fault, we again have to throw an exception, invoke the operating system, and go and handle it. Okay, so now we have our translation to a physical address, and we can access the instruction cache, which has everything mapped in physical addresses. Okay, if we got to cache it, everything is good, we can continue on to decode. If, on the other hand, we had a cache miss, now we have to go over to the memory controller and really fetch our cache block from DRAM, bring it into the instruction cache, and then we can continue on to decode. And this could be a very long type of a process. The only other thing is that we have to do this again when we go and we have loads and stores that are going to go to the data cache. So this is really a headache. We just kind of killed our whole CPI. Virtual memory, therefore, is really, really, really expensive. It's so expensive that seems not to be very feasible. We worked really hard to, have all these non-cache misses and so forth, but in a single level page table, each reference becomes two memory accesses, DRAM accesses. With two level page tables, we have 3 memory accesses, and we saw that this can get even higher for like 64-bit machines and so forth. We just totally killed our performance. So any suggestions? And we said that indirection is supposed to solve any problem in computer architecture. Unfortunately, indirection doesn't really help here, but there is a second solution. The second solution is caching, of course. Let's just cache our address translations. If we store our recent virtual address to physical address mappings on the chip, we don't have to go to DRAM every time. And this is called a translation Lookaside buffer, which is the subject of this part of the lecture. So what is a translation Lookaside buffer? It's a cache of virtual to physical address translation. That's all it is. So we have a memory access request. The memory access request is going to provide a virtual address to the TLB. If we had a TLB hit, in other words, the translation was cached inside our TLB, then we just provide the physical address directly without going out to DRAM. If we got a TLB miss, then we have to go and do our page table walk, which is going to be quite expensive. So what we know is that we're going to have this TLB on our critical path, and therefore it has to be fast. Unfortunately, fast means that it has to be small. Luckily, a really small TLB can be very effective. Usually, you'll have something like 16 to 512 entries in a TLB, and towards the end of the lecture, we'll see a real world example of this. So let's see how this works in practice. Here we have a really small 2-entry TLB, and we have 2 tags stored inside our TLB with their translation to physical page numbers. And we see that one of them is valid, one of them is not valid, and neither of them have recently been accessed. So we come in with a virtual address access, which is going to this 0003204 address. And what we're going to do is we're going to take the page number out of that. This is the virtual page number, and that's going to be our tag. Go and be compared against our tag. And we see that 00003 does not appear inside our TLB, and therefore we have a TLB miss. We need to go do a page table walk. So we're going to go and find page number 3 and see what that is and load its translation into the TLB. So we found page number 3. We loaded it into the TLB. Now in our tag, we have 00003, and which is our virtual page number, and we have the translation, which is the physical page number over here. We also say that this is valid because it is pointing to DRAM, and it was recently accessed. So now we go and we access the same address again, and we take that and we see that we get a TLB hit, and therefore we can directly take our physical page number, add to it the offset, and we can go and access DRAM. So minimizing TLB rate is critical. Again, this is going to be happening once and often twice on every instruction that we read. We need to access the TLB. And if we get a miss, we have to go do a page table walk. And if it's really bad, we have to go do a page fault as well. So minimizing the TLB miss rate is critical. We want it to be, way lower than 1%. And therefore, we're going to usually use something that's fully associative, maybe 4-way or 8-way associative, but really as much associativity as possible to limit the miss rate. Another thing is we're going to use a replacement policy that's going to be very useful. LRU tends to be too expensive to do in hardware, so we're probably going to use something like random or FIFO. And we can also use a second level TLB. So these second level TLBs aren't exactly in direction. It's just going to be that we're going to have one really, really fast TLB that's going to be small, and then we're going to have another level of TLB, maybe another few levels of TLB that are going to be bigger. They're going to take longer to access, but at least they can reduce the need to go out to DRAM. So they're going to increase the hit rate, even though it may be a bit slower. And we can also use larger page sizes, which will also reduce the TLB miss rate. So how does our processor now look with the TLB inside? So now we have two TLBs in the pipeline. We have the instruction TLB that's going to get the virtual address and hopefully provide the physical address. Only when we get a TLB miss, then we have to go to the page table walker, fill the check for our page fault and protection violations, and bring our new translation into the TLB. Okay, then again, we have a data TLB. So on loads and stores, we can provide a virtual address and go get the physical address from the TLB and only go to the page table walker when we get a TLB miss. So this, what we saw before, is called a physically indexed, physically tagged cache. And in this case, the CPU creates a virtual address, which has a tag, an index, and an offset, as we saw earlier in the lecture. Okay, and what we do is we provide that to the TLB, which performs a TLB lookup, and if we get a hit, we provide the physical address. If we got a miss, we have to go get a page table walk, and eventually we'll get this translation into the physical address. The physical address then is used to access the cache, and if we get a hit, then we provide our data. If we got a miss, we have to go and fetch the block from the next level. And this process is very slow. So we had to first go through the TLB, then go through the cache. And even if we didn't have a page table walk or a cache or a cache miss, we still had to go through these two things serially. And this significantly slows down the memory access. Really, this will often become the critical path of our processor. So the question is if we can make it better. And the answer is, yeah, we can use what we call a virtually addressed cache. So why don't we just access the cache with a virtual address? Now we only have a TLB lookup if we have a cache miss. So our CPU provides a virtual address. We have the virtual tag to tag the instruction cache, and therefore we can just provide a virtual address. If we have a miss on our virtual tag, then we go to the TLB and we get the physical address and go and get it from DRAM. Well, this type of a cache is called a virtually indexed, virtually tagged cache. So does it work? I mean, that solves all our problems, right? Well, unfortunately, not really. Yes, I am saying that, but it is done in certain processors and has been done, but it's really complicated. Why? Well, first of all, permissions are stored in the TLB. So if we want to know about read, write, and execute permissions, they're in the TLB. They're not in the cache. So I guess we have to add some metadata to the cache or something in order to do that, or else we don't have any protection. The real big problem is that different processes have the same virtual address. This is called a homonym. So that means that when we access a virtual address, it's going to be for that particular process. If we go and load another process, what we call a context switch, and we'll be discussing in the next lecture, we would really have to flush the cache. Another way to do it is to add IDs for each of the cache entries. So that's one way to get around it with, again, some other overhead. But really, a problem that we can't deal with very well is what we call aliasing. That's when two virtual addresses point at the same physical address, and it causes data to be stale in the cache. I'll show you an example of that in a couple of slides. So the question is if there is any way to get the best of both worlds, both have a fast cache and have something that doesn't suffer from these problems up above. So of course there is a solution. We understood that we almost always have to use physical tags. Physical tags enable process isolation of virtual addressing. But the TLB is serially, in the pipe, twice in fact. So it really slows our processor down. So the question is if we can hide that access to the TLB in some way. And the answer is a virtually indexed physically tagged cache. That's a real long word. We usually just call it a VIPT cache, therefore. So let's see how this works. We're always going to access the physically tagged cache. So we take our virtual address, which, remember, when we're talking about caching, has 3 parts in it. It has the offset, which is the cache line offset, typically something like 6 bytes. Then we have the index and the tag, which are divided according to the associativity of the cache itself. So what we're going to do is we're just going to take the tag part without the index part and use that to access the TLB. And the TLB will give us the physical address, which will include, again, a tag, a physical tag, and the index. Then we're going to take the index part of the virtual address and use that to look up the cache. So these are completely separate from each other. So we can use them at the same time. We don't need the physical translation in order to access the cache. We can already access the cache at the beginning when we have our virtual address without accessing the TLB first. So this is done in parallel because it only uses these bits which do not overlap with the tag that we use for the TLB lookup. So now we got the tag and we got the tag of the physical address, and we got the tag from the cache lookup, and we can compare them, and if they're equal, that means that we got a hit, and we can send the data to the CPU. If we got a miss, then they're not equal, and we have to fetch the cache block from the next level. So this way, we perform the TLB lookup and the cache lookup in parallel because we have the bits that we need to access them at the same time at the beginning from the virtual address, and we don't have to wait for the TLB lookup in order to translate them. And this really hides the access to the TLB lookup. And this is the way that most L1 caches are built today, but this actually it limits the index size. Using a larger cache tag than the index will lead to aliasing, and we'll see that in the next slide. So I think that this slide will help us kind of understand the mechanics of the VIPT caches better. But first, I'm going to start with the aliasing problem in a VIVT cache, in the virtually indexed, virtually tagged cache. What happens when we have 2 virtual addresses that point to the same physical address? Well, this can easily happen. We can go and try to access the DRAM from 2 different processes, for example, and therefore we can, have 2 different virtual indexes which will be pointing to the same actual physical address. And the problem with this is that if we go and store to one of the virtual addresses, it's going to overwrite this. And if we have a write-back cache, that's going to stay here, and it's not going to change in the other copy that we have inside the cache. And therefore, if we, for example, load data from the other virtual index, the virtual tag, what's going to happen is we're going to get stale data, and that is called aliasing, and that's something that we are not allowed to have. So how does the VIPT cache overcome this? It does it by storing and comparing the physical tag, not the virtual tag. So inside our cache over here, we're going to have the physical tag and not the virtual tag. So how does this work? Well, basically it knows that we have larger DRAM pages than we have cache lines. So in our typical example we've been running with, we have 12 bits for the page size offset, but we only have 6 bits for the cache line offset. And therefore, there are another 6 bits that do not overlap between the page size offset and the cache line offset. So therefore, our tag over here, it has an extra 6 bits that it doesn't need to translate. So what we can do is use these 6 bits in order to index our cache, and then these 6 bits do not need to go through translation right now. So we took these 6 bits, we saw that we were pointing at this cache line over here. In this cache line, we had a physical tag. We took out this physical tag, brought it to the comparator, which we compared to the translated tag from virtual to physical that we got through the TLB, which happened at the same time that we were accessing this. And then we do the comparison between the tag that we got from the translation from virtual to physical in the TLB and between the physical tag that we had stored in the cache that we used the same amount of time to fetch it from the physical tag. And if we have a hit there, it means that this was the correct data that we wanted, and we can go and use the data that we also fetched from the cache at the same exact time. And this is because each one of these cache lines, it doesn't point to several spaces. It's not a virtual line, it's a physical line. So this is really equal to whatever is stored over here. Okay, so we can do this TLB lookup in parallel to a cache access, and we don't have this problem with aliasing. However, this is limited. So assume that we have a 4 kilobyte DRAM page and 64 bytes of cache line, which means that we have a 12-bit page offset and a 6-bit cache block offset. as we saw before. So we saw that we only actually had these 6 bits that could be used for the translation. If we used an additional bit, then it already would have to go through translation to physical tag in order to access the cache. That would cause aliasing. That means that it could be in 2 places, basically, and that's not something we can deal with. So we are limited to using these 6 bits, and therefore our cache can only be 64 entries deep. Okay, if it's 64 entries deep and we're direct map, that means we only have 4 kilobytes at the maximum inside our cache. And 64 kilobyte, we only have 4 kilobytes maximum inside our cache. And 4 kilobytes is really a small cache. I mean, we're talking about things that we want to have megabytes of cache, right? So how can we make that bigger? Well, we can increase associativity. For example, if we have 2-way associativity, so each of our indexes can have 2 different ways inside them. That means we can have 4 kilobytes in 2 different places, and therefore we can get to 8 kilobytes. We can use, 2 to the 7 entries for that same 6-bit access to the cache. And increasing associativity farther enables us to really increase this cache size from the 4 kilobyte limit that we have with our 12-bit page size and our 6-bit cache block size. We can really increase it farther. So that's why we'll see in a second that we have typically high associativity, something like 16-way in inner level caches, even though we saw that usually additional ways don't actually help us with hit rate. So let's look at a real-life example of this, and we'll take the recently released AMD Ryzen 7000 or Zen 4. So we can look at the architecture over here that was released in November 2022. So there are many different versions of this, but if we take some of the specs, we can see that we have these cores. There can be up to 96 cores on one of these processors, and they actually have another level of cache that we didn't discuss, which is a level 0 cache. In this case, it's an instruction cache, so it's kind of like an instruction buffer that can buffer up to something like 7,000 instructions inside this, so it can really have quick access. This will probably be something like registers or something that are holding this. Okay, and then we have our 2 L1 caches. So we have our L1 instruction cache and our L1 data cache. And guess what? They're 32 kilobytes in 8 ways. Remember our 4 kilobyte maximum size with 64 byte cache lines? Well, 4 kilobyte times 8 ways, that gives us 32 kilobytes. And that's why that is the size of our L1. We would like to have a bigger L1 than that, but really our aliasing probably limits us. So we have our L1 instruction cache and we have our L1 data cache, and they're both going to be 8-way in order to provide us at least that 32 kilobyte size. Then we have our L2 cache, which are going to take more cycles to access, and it's going to already have between half a megabyte to a megabyte for each core. But put it this way, each of these cores, they have their own L0, L1, pair of L1 caches and L2 caches. These are per core share, they're just personal to that core. It's also going to be 8-way because 8-way, I guess, gives a low enough miss rate, and they're all going to be write-back caches. Then we have an L3 cache, and the L3 caches are going to be huge, and it's shared between all of the cores, and it can be up to 384 megabytes in the highest end architecture that we have here in this series. It's going to be 16-way, and that's because it's shared by all these cores. We want to give it as much associativity as possible, so really we can put any cache line in any place over here, and it's going to use write back as well. Then, of course, we have DRAM, and this type of an architecture can support up to 6 terabytes of DDR5 5200 DRAM. It also supports page sizes that can be 4 kilobytes, which is the typical one, but it can go up to 1 gigabyte page sizes. And of course, we have to not forget our TLBs. So our instruction TLB is going to be 64 entries in fully associative, where our data TLB is already going to be a couple more entries, 72 entries, and also fully associative. But that's the L1 instruction in data TLB. We also add an L2 instruction in data TLB. We showed before that these guys are just going to be bigger TLBs that are going to take more time to access, but they're going to at least limit our page walks. So this is going to have 512 entries, and it's not going to be fully associative, but still it's going to be 8-way associative, and this is going to be 3,000 entries, and it's 24-way associative. So that's kind of a real-life example, and thanks to Wikichip for detailing this. It's really hard to find this type of data anywhere. So just let's summarize virtual memory. Virtual memory adds a level of indirection between the program and the memory. It enables us to provide unlimited memory to each process. It isolates programs, gives us a full address space, protection, and data sharing. It eliminates fragmentation. But accessing memory using virtual memory is really expensive. We first need to access the page table to find the physical address. Then we need to access again to retrieve the data from DRAM. In multi-level, we need to access DRAM a couple more times. If the page is not resident in memory, we get a page fault, and that's really, really bad. It's really costly. So we can make it faster by caching virtual addresses to physical addresses, and this we get by using a TLB. So a PIPT cache requires translation first, so we have the TLB really serially on our critical path, and so it's really slow, and we shouldn't really use that. The VIVT cache, that's really fast, but because it doesn't need translation, but it's kind of impractical with aliasing and with the other problems that we mentioned. And finally, we have the VIPT cache, which is really what's mostly used in today's processors. And it enables us to parallelize the TLB and cache accesses, and so it's fast, but it really limits the cache sizes, and therefore we see that our L1 caches are going to be pretty small. So thanks to all these references, and I hope you guys understood now what virtual memory is and what caches are and all about the memory hierarchy.